Hello, long time no see. Welcome back to 61C. We are getting into a brand new module. This time we are talking about parallelism. So we are still continuing our quest to make a better computer and to run our applications faster. So we have learned some of the software techniques that are helping us with that, but we spend most of the time trying to build a better computer and understand the principles how these better computers are built. One of those principles is the use of parallelism, and we have encountered parallelism already. We have encountered multiprogramming as a way to better utilize a processor while it's waiting for data to come from DRAM. We can perform some other task. We have seen pipelining as a way to increase the performance by working on multiple instructions at the same time in a pipeline. And that was the primary way how people tried to increase performance of processors in, say, the 90s up to early 2000s. We kept building deeper and deeper pipelines and simultaneously use that to crank up the clock frequencies. But as a result, the power kept shooting up in every processor generation, and that was not sustainable. We had to do something different. In order to stay under reasonable power limits, people explored the dimension of using parallelism. And in this case, we are going to take a look at how do we work with parallel data. What does that mean? Simply, we often in our applications work with some sorts of vectors, and we can perform vector additions, in this case, in parallel if we have multiple units that are capable of adding multiple elements of a vector at the same time. There are many opportunities for data parallelism out there. One of them we have already encountered, and it is one of the most popular workloads nowadays, which is machine learning inference. In machine learning inference, we often start with something and we would like to perform classification. In this case, we can start with an image of a cat and would like to say that's a cat and not a dog. The way how we do that is by going through multiple layers of classification, feature extraction here, that in their essence are fairly parallel. They could be convolutions, matrix to vector multiplications, or matrix to matrix multiplications. And after a sequence of those classification steps, we can say that this image, that there is a cat in this image and not a dog. And in turn, if we feed to our neural network an image of a dog, it'll tell us it's a dog. If we feed handwritten numbers, it'll be able to tell us whether that number is an 8 or a 9. There is parallelism here, both within each layer, but also we can process multiple layers concurrently. We have introduced matrix multiplication. Matrix multiplication is not just common in neural nets. It's one of the most common operations that we'll encounter in engineering, data science, and many other application domains. Generally, we'll find it in image filtering or blurring or noise reduction, and many of the machine learning kernels. But it's not a modern type of workload. I mean, it has been so prevalent in engineering that it has been supported in languages since long time ago. For example, there was a language, one of the first languages that I've learned as a student was something that is called Fortran. You guys might not have even heard of a Fortran. Tell something a little bit about my age. Fortran was a common language for engineering applications in the past up to probably early 2000s, when it was basically replaced in most of the domains by C. It took C a while to displace Fortran, legacy Fortran, from everywhere in the world. So in Fortran there was this instruction which was dgem, and dgem is a double precision floating point matrix multiplication. So it was as prevalent or as important that it needed its own instruction. Just to quickly recap our matrices, because it will be helpful in understanding how we work on them a bit later. Here is an example of a square matrix with I rows and j columns. Important thing to keep in mind is we generally can't store this matrix as like a square matrix in a memory or on a disk. It is generally stored sequentially. So we have a choice here whether we would like to store it by serially by rows or columns. Generally it is serialized by columns. So in this case, the first element in the matrix A00 will be followed by the second element in that column, A10, and then we would store them all up to AN-10, and then we would continue with the second column, A01, store all of them up to AN-1, 1, and so on. All right, and what does the matrix multiplication do? Well, it's if we say that we would like to multiply two matrices A and B and store the result in a C, what we are essentially doing, we are performing an iterative process that computes elements of a resulting matrix Cij as sums of pairwise products A, Ik, and bkj. The inner coefficient k is the same, and that basically means that the number of columns in matrix A has to be the same as the number of rows in matrix B. That's the only way how the matrix multiplication is valid. So when we would like to find this element Cij, we would perform pairwise multiplication of all the elements in row I with all the elements in column B and sum them together to get the element Cij. Notice that all these multiplications of elements Aik and Bkj can be performed concurrently, and then we would just add them together. So we're going to look a little bit more into that after a quick break.